All right, welcome back. So, if you recall from our last light board discussion, we emphasized the fact that these area regions that lie between the graph of a function and the horizontal axis are actually quite meaningful. If this graph that's sort of sketched here with f of x was a velocity function, well, then the signed area that lies beneath that velocity function, between that velocity function and the horizontal axis, would correspond to, or at least relate to, the distance that was traveled by the object, effectively the change in position over the course of time. And so that's, well, meaningful information, right? And so because these area regions between functions graphs and horizontal axes are meaningful, well, it would be nice to develop some mechanism by which we could, well, at least approximate the area of these regions. Because, well, as it sort of says up here at the top, how to approximate amorphously shaped regions of signed area, the idea is that, well, not every function is so cookie cutter in shape that the region between its graph and the horizontal axis is of a kind that we would have a geometric formula from like high school geometry for. So maybe your function is a line and then you just have sort of like a trapezoidal region and you could use the formula for the area of a trapezoid. Maybe your function sketches like a semicircle or something and then you could use a formula for a circle. But really, most often than not, if you're just imagining a function in general, you would have something like is sketched here where you have this amorphously shaped region and, well, the signed area of that region is meaningful, and yet how are we going to compute the area of that region? It's not exactly clear to this point. So we want to develop a strategy for how to approximate the area of these regions. And well, the strategy is ultimately to break this amorphously shaped region into regularly shaped subregions. So that is our strategy. And well, let me just write it here. The strategy is to use regularly shaped rectangles to do so. And so what we're going to do is we're going to essentially partition our interval from A to B into a bunch of sub-intervals. So we've got this interval from A to B. As I've drawn it here, it looks like there's 1, 2, 3, 4, 5, 6 subregions, sub-intervals that we've partitioned this entire interval into. And then on each of the sub-intervals, what we're going to do is we're going to place a rectangle. But instead of placing just any rectangle, we're going to place a rectangle which is going to appropriately approximate the signed area between the function's graph and the horizontal axis by making sure that each rectangle on each of these subintervals is going to be exactly as tall as the function is tall. Now, on any of these subintervals, the function will be varying in value. So we're going to have to pick a convention by which we establish the rectangles of interest. And so what if, let's say, we just used the right endpoint of each subinterval to determine the height of a rectangle? Well, if we did, we would get a picture that looks like so. So I'm taking the right endpoint of each subinterval, and I'm drawing a rectangle exactly as tall as the function is tall at that point. And what you can notice is, if you look at the total area of these 6 rectangles, is it exactly the signed area between the function's graph and the horizontal axis? Well, it's not. There are sort of like little voids in here that you can observe where the rectangle does not exactly measure the signed area between the function's graph and the horizontal axis. However, those rectangles do a pretty good job. So using regularly shaped rectangles, we can approximate. We're not looking for an exact value for the area under an amorphously shaped region just yet. We're looking for an approximate value. And well, if we added up the area of these 6 rectangles, we would get our approximate area. So approximate area is the area of rectangle 1 plus the area of rectangle 2 out to the area of rectangle 6. So we add up the, where AI here is the area of the ith rectangle drawn. So just add up the area of our 6 rectangles. That gives us the approximate area between the function's graph and the horizontal axis. And well then, think about each of these areas. Well, each of these areas is just a rectangle. So to compute the area, you just do width times height. And well, if you think about this, that's, I suppose, only so complicated to compute as well. So the width here for each of these, because the way that I could write this out, we could do like width 1 times height 1, width 2 times height 2, all the way out to width 6 times height 6. That would be the area of the 6 rectangles. And well, the width of each of these is actually known, because essentially what we did is we just took our region from A to B and we chopped it into 6 subregions. So notice the width of each rectangle, let me write this up here. The width of each rectangle, in this case, is just b minus a divided by 6. And in general, the width of each rectangle that you would consider after partitioning your interval from A to B would be just b minus a divided by however many rectangles you have, right? Because b minus a is the total width of the interval. And then if we divide by 6, what we're doing is we're taking that total width and just breaking it into units of 1/6 the total length, which would in total give us the width of the whole interval whenever we consider all 6 widths. But for each individual width, it's giving us precisely the width that we need. And so frankly, each of the widths that we get down here is just b minus a divided by 6. So I'll leave the heights to plug in a moment. But right, each width is identical. Each width is just b minus a divided by 6. And then what about the heights? Well, maybe it would be worth our while to label the points that we used to, on the x-axis to determine the height of the function. And let me just call this point here x1. That is the first point that we evaluated off the function. And this next point x2, and this next point x3, x4, x5, and x6. These were each of the x coordinates where we evaluated the function at each of these x coordinates. At x1, we evaluated up to the function at f of x1. At x2, we evaluated up to the function at f of x2, and so on. And so what was the height of our first rectangle? The height of our first rectangle was just f of x1. The height of the second rectangle was f of x2. And the height of the last rectangle was f of x6. The 6 here, because there were exactly 6 rectangles, that 6 shows up in the denominator of our expression for the width of each rectangle. That 6 also shows up in terms of the number of points from the domain that we sampled to evaluate the height of our function's graph at that point. But yeah, what you notice here is essentially the sum of the areas of the 6 rectangles then provides us with, well, that approximate area for our functions, for the signed area region between the function's graph and the horizontal axis. What I will say is, if you notice this computation, this sum takes a very regular form. There is a common notation that is used, so notation, to describe a sum which is so regular in terms of its form. We often use what is referred to as sigma notation to describe such a sum. And so when we use sigma notation, the way that I like to think about this is that the number on the bottom sort of tells you what to start at with your variable I, and the number at the top tells you where to stop. Looking at each of the terms in this sum, each of the terms are of the form b minus a over 6 times f of x sub I. And so if we look at this expression for the, in sigma notation, what we're saying here is sigma is going to denote a sum, we're going to start at I equals 1 and go all the way up to I equals 6. Looking at this expression, starting at I equals 1, the first term of this sum would be b minus a over 6 times f of x1. Note I here is playing the role of 1. Well then, after we look at b minus a over 6 times f of x1, we now let I go up to 2, and then we go b minus a over 6 times f of x2. Note, these are precisely the terms within our sum that we saw previously. And well, in fact, those x sub i's go precisely from x1 to x2 all the way up to x6, which is precisely why our summation could be expressed from I equals 1 to 6. So here is a concise notation to describe the expression for our approximate area. Because the expression was so regular in its form, using sigma notation can be a really nice way to concisely articulate what we're seeing within such a sum. And just so that we have an example to see this in sort of precise detail, what if we do like sum I equals 1 to 3 of I squared, just to get a feel for this notation? Well, here we're starting at I equals 1, we're ending at I equals 3, and we're looking at the expression I squared. So at I equals 1, we'd have 1 squared. Now we go up to I equals 2, that would give us 2 squared. And then we go up to I equals 3, and we'd get 3 squared. We stop at I equals 3 because the top number on our sigma tells us to do so. Ultimately, I think of that bottom number as where you start, the top number is where you stop. The sigma denotes a sum, and then we are just mechanically plugging and chugging the values in accordingly. Let's see, 1 squared is 1, 2 squared is 4, 3 squared is 9. Put it all together, we'd get 14. So, right. What we've got here in principle expressed on this board is a mechanism by which we can approximate the area of an amorphously shaped region. Take an interval from A to B, chop it into some number of pieces, and then on each piece, draw a rectangle exactly as tall as the function is tall. Evaluating the area of each of those rectangles and summing up will give you an approximate value for the signed area between a function's graph and the horizontal axis. It's not perfect, right? There's these little voids where we don't have the area under the function f of x described exactly by our rectangles. But within some reasonable margin of error, we've got a pretty good mechanism by which we can compute the area of these regions that we desire. So at least for now, this is a nice place to start, and maybe I'll sketch through an example just to sort of further edify this idea, and so that we can see it in specific form. But for now, this at least gets us started.